Right now we want to introduce you how to do the standing wave experiment. Yay! This experiment has two parts. To study a vibrating string tension and its wavelength relationship at this measurement and calculation short frequency of vibration. We know that the formation of a standing wave on short is equal, but superimposed in direction opposite to trains of waves. By a fixed porting along the short, each separated by a half wavelength of distance from these points, is always static. These are the nodes. The internode points vibrate and have maximum amplitude in the middle of the two. On the vibrating string, all points of the adjacent phase with vibration and all pass through the central location at the same time. But how to do this? We want to do this using the Meldes experiment. For this experiment, we used a short endpoint connected to the electric tuning fork to establish a standing wave. In here, the tension is generated by the wave connected to the other end of the short. The wave generated by the tuning fork vibration proceeds to the other endpoint and reflects back to create a series of accurate standing waves. The nodes appear in every half wavelength distance. Therefore, the wavelength can easily be measured, and the strings on the rate of wave B can be obtained as following. The formula of wave B is equal to the square root of F, that is the tension of the screen, over the density of the short. But we know that the wave is also the frequency times lambda. So if we combine these two formulas, we obtain that F is equal to 1 over lambda times the square root of the tension over the density. Okay, so we end with the theory things. Let's do this now.
So blue, me pressing through. I can't forget the day we met. Your smile so bright, it made me swoon. Our love is like a summer's day, hot and endless in a magic way. Whenever I see you, all I can think is my summer love. Been waiting for you, my love. My summer love. Been waiting.
Yay! The objective of doing this part is to explore the relation between the speed of the compression longitudinal waves and the characteristics of the springs. We want to use the same theory as the first part of the video, but now applying it to a spring. Yay! When we apply vibration to a spring, these particles vibrate parallel to the direction of the motion of this wave. The waves of a spring are not the same as the short's waves. In the picture, we can see that every node has a refraction and a compression part. We can use that information to identify the nodes and thereby take the correct measurement. We separate the method in parts A and B. In the part A, we're gonna do the Meldes experiment that use a spring endpoint connected to an electric tuning fork to establish a standing wave. Ooh. Then, combining some formulas like Hooke's law, wave velocity, or relation between frequency and waves, we can obtain the value of our spring's constant. For the part B, we use the Hooke's law to obtain the K value of this spring. We just need to use different masses to prove that, and then compare this K with the previous part.
I can't forget the day we met. Your eyes so blue, me pressing through. I can't forget the day we met. Your smile so bright, it made me swoon. Our love is like a summer's day, hot and endless in a magic way. Whenever I see you, all I can think is my summer love. Been waiting for you, my love. My summer love. Been waiting for you, my love. style, your look, your everything. When I see it all, I knew that you were mine. I'm in love with your hair, your lips, your silver.